Now we have four 25-minute talks on strong gravity. And the first talk is going to be by Javier Garcia on reflection spectroscopy with STROBE-X.
Thank you. Thank you for having me here. I just came down from a back hole last week, so as any respectable scientist, I was leaving the preparation of the simulations and this talk for the very end, and then I got sick, so this is the best I could come up with given the circumstances. So I apologize for things not being super great. So I'll try to talk about just a few points that I thought might be relevant for STROBE-X and what I think, why I think STROBE-X might be an exciting mission especially for reflection spectroscopy. So I'm not going to say much about it because I think you all know what reflection means, but just the cartoon picture that we think most of the X-rays are coming from a very compact region near the black hole, and when these X-rays they go to the observer, you see the power law emission, but if they shine into the accretion disk, an optically thick disk, then you'll see different components of reflection. If the reflection is far away from the black hole, you see tons of atomic lines, fluorescence, and edges, and things like that. But if it happens near the black hole, then you see the effects of the relativistic blurring kind of smear out the whole thing. So these effects are important because we can use them to measure things like the spin of the black hole. So this is the typical stellar point for reflection, but I'll say there's a lot more that we can learn through it regarding the geometry and how the illumination occurs, and how the accretion disk evolves in the case of black hole binaries, for example. So there is a lot of information you can gather with this technique. So I'll talk about a few points. One is I was thinking about how important it is to measure the temperature of the corona, and this is typically done by looking at the cutoff at high energies. If you ever heard a recent talk by Andy Fabian, he's talking a lot about it. There is a lot of our new results that have derived from NuSTAR, and this has to do with what I just said. You just see a cutoff at high energies in the power law. And if you think that this power law is being produced by a comptonization in a hot gas of electrons, then this temperature is related, the cutoff is related to the temperature of the corona. And this is just a sample of some of the determinations for various AGNs using NuSTAR. You see there is not a clear, sorry. There's no correlation with the photon index there. And one question I was asked a few years ago is, why the hell do we see that with reflection, you can sometimes constrain this cutoff to energies much larger than the bandpass of NuSTAR? So start looking into that, and what happens is, when you change the cutoff in the illumination, so you have a power law that illuminates the disk and that produces some reflection. If you change the cutoff, obviously you're going to change the way the reflection looks like at high energies. This is just a sample of reflection models for two different ionization parameters. And you see by changing the cutoff from something like 20 kV to 1 MeV, you have all this difference in the quantum hum. But the other thing I notice is that it's not just the shape. You're changing dramatically the energy budget that you put into the gas, so it affects the ionization balance. These are temperature profiles for those calculations. So it happens that it also changes things at softer energies. And the changes are in a way that they cannot really mimic by just adjusting the amount of flux or ionization. So these are now comparisons of, these are the input power loads that are used for the calculations. These are the reflected spectra for two different cutoff energies, 300 kV and 1 MeV. And if you're trying to detect what's the curvature and what is the cutoff with null star, you're going to have trouble because this is where the null star coverage ends, and this is where the curvature starts. But it turns out that the reflection is sensitive to it, as I just mentioned. This is the ratio of these two models. And you can see there's a lot of different things happening at the softer energies. So we ran simulations and find out that seems to be the case. You can constrain the cuts to very high energies if you have real quality data. And things look even better if you included the softer energies for the reasons that I just mentioned. I rerun quickly the similar simulations with the STROBE-X responses, and we can essentially do the same sort of deal in a fraction of time. Maybe what you can do with null star 200 kiloseconds, you can now do with 20 kiloseconds. So, so I think that's very exciting. That's going to probably extend our sample quite a bit. The other thing that I just realized is, and I'm not sure if I quite understand this, the background in the lab seems to be very, very high all the time, much higher than the source counts for relatively faint sources. So that might have to do with me being stupid in how I do the simulations. I'm just using the same exposure time for the source in the background. But regardless of that, I also realized that the effective area, at least the way it's in the files, is still pretty large at higher energies, higher than 30 kV. And I'm not sure why we're stopping there, and we can discuss that at the end, but I did.
That's because the collimator becomes transparent somewhere around there. And that's something that there may be some design options for that all looked into it.
Yeah, I would suggest not to consider energies above 30 kV.
I see.
The collimator would be transparent, so you basically be an open.
I see.
That was meant only for getting bright events from outside that you could do, like a burst or market of that.
I see.
So I would suggest not to consider that.
Then forget about the blue light, the blue stuff. Because I just extended it to 80 kV just to see what the effect was. It's not a large effect, but it obviously makes things a little bit better because you have a better coverage if you will go to 80 kV or so, despite the high background. So another thing that I'm interested recently is this really old and almost boring problem of the sub-excess in AGNs. Some people might say it's a lost problem. Some people might say it's solved. I don't think it's solved. I don't think we understand it. And I'm not going to get into it too much, but if you look at some AGNs, you typically see a sub-excess at low energies. This is one particular case I've been looking at, Markarian 509. This is data with Susako and Nullstar, simultaneous. It is not very clear what this emission is entitled for. There are some possibilities that include, well, people initially thought it was thermal disemission. The problem is you see it more or less at the same energy for almost every source regardless of the mass, so that kind of doesn't work out. It could be a warm quantization corona, and I'll talk about what that means. It could be relativity reflection, possibly high density from a high density plasma, and there could be something else, some diffuse emission that we don't know. So I'll disregard these two and just talk about the two in the middle, which are the ones you see mostly in the literature. And the warm corona picture is essentially saying, well, you can come out with this soft emission if you think there is a warm corona sitting on the top of the accretion disk. And by warm, I mean something about 100 kV temperature, sorry, half kV temperature, and a very large optical depth. So you need these two kind of quantities to make up for something that looks very soft, kind of almost like a multicolor black body component. To me, that doesn't make much sense, because how the hell do you do you have a corona with an optical depth of 15 or 20? That seems to be a little bit crazy, but models allow you to do that. People feed them and write papers, and they say hooray. I did the same. So this is the fit with that model, the warm corona model, and distant reflection, and it does a great job indeed with that data. But you can also do a similar, very good job with relativistic reflection. And these are new models that include a higher density effects in the atmosphere, which I'll mention a little bit more later. But essentially, I cannot distinguish between these two, not with this data. So we don't know which one is correct. And if I just do the simple exercise of running a STROBE-X simulation with the same flux and the same exposure, it will be extremely clear which one. At least it will be clear that they're very, very different to the details. So this is just running simulation with one and trying to fit with the other one as best as I could. It was impossible to get a decent fit out of it. So I think the XRCA will be very powerful precisely because of that, because there is a lot of things going on as soft energies, the cutoff, the effects of the cutoff, the soft excess, high density reflection models. For example, traditionally we've been running reflection models with 10 to the 15 centimeter cube, some God-given number from 20 or 30 years ago, because we thought that it didn't matter too much what the density was doing. What it mattered was the ionization parameter. And that is more or less true at the iron line, but when we start looking again and running models at much higher density, what happens is that the free emission, you have a lot of extra heating from free emission, and that produces a very strong flux excess soft energies with a whole bunch of features, as you can see. So these are all blur model, right? So there's no GR in here, but precisely this is pointing, and these are the kind of models I was using before. This is pointing to maybe we've been doing things a little bit stupidly in the past. And these are another couple of examples of just simple tests of using high density models on extreme sources like IRIS 13224 or 1HO707, which are very peculiar AGNs, a very steep power loss, very high iron abundances, and it looks that the high density models are going in the right direction, but we need better data to understand the constraints. So just a quick slide on spin measurements. This is applicable to, of course, black hole binaries and AGNs. I didn't have much time to do an extensive simulation survey, but I run a few simulations, and what I find is usually for high spin it's very easy to constrain the spin because you have so many counts. You'll have to go to very, very faint sources to start running into trouble.
Assuming your iron line fitting,
This is
getting spin.
Yeah, this is all with reflection spectroscopy, yeah. So I'm sorry that I don't have anything much intelligent to say here. I did look very quickly at the de-scoping of the lab between the 200 and the 300 EV resolution, and it has some effect, very low spin, but other than that, I don't think it's a major issue. And I will now show some results we're getting from RXT work, and what I've learned so far is a whole lot of counts beat resolution when you do a reflection spectroscopy. I think that could summarize more or less what I wanted to say. So in black hole binaries, there is this thing that I've been calling the controversy of the distruncation. If you know what a Q diagram is, this is for GX339-4. It's a black hole binary, very well known, very well studied, and this shows the hardness in X-rays versus the count rate in the PCA. This is hard state, this is soft state, and in the soft state there is a pretty good consensus that the accretion disk should be at the ISCO, the inner most stable circular orbit, and it's quite stable there. And a very low luminosity, there is also pretty much a good consensus that that this must be truncated because you have, you have such a low accretion rate that you should be seeing something like an ADAF. But then it's not very clear what happens here before the transition. As it rises in luminosity in the high state, what we're seeing is that this is evolving, it's filling in, getting closer to the ISCO. But there's still a lot of questions of how close does it get before the transition and what is evolving really. We look at, as I said, to RxD PCA data, combined data for all this track in the higher state. We started 6 combined spectra that look really good. As you can see, they have millions of counts in each spectra. You can see all the reflection features very well. Maybe this shows it better. With the limited resolution of the PCA, you can very well resolve the iron line, the KH, and the Compton comp. So unless you're looking for very small features, I think low resolution, but a lot of counts again can give you a lot. So we were able to fit this very high signal to noise data very well with the reflection models that we have, and this is what summarizes the controversy in the distruncation. There are other studies done with XMM in the timing mode that have reported at these are almost simultaneous observations, or at least at the same luminosity states, and they're coming out with truncations of hundreds to almost 1,000 RGs. This is not. This doesn't work out with what we're seeing in the PCA. We need the disk to be much closer, perhaps just a couple or a few RGs from the ISCO to come out to reproduce the broad iron line that we're seeing. So the red points are what we derive with the PCA. All in green is previous iterations with Suzaku. They kind of follow the same trend, but you have all these cluster of points. They're all coming from the same data. They're all coming from XMM in the timing mode. We're now starting to get convinced that the timing mode has calibration issues, but to make things even muddier, there are also some timing analysis that had derived some estimates for the inner radius from either QPOs, these are the QPOs, these are from time lags, and they seem to agree with the high truncation, so that this has created a lot of discussion in understanding what is going on. And I think, a lot of people won't necessarily believe PCA because of the limited resolution, no matter what I say. So broadband coverage and better resolution and better effective area, of course, will help to resolve this issue. And this is, here I'm trying to show how STROBE-X will be able to maybe say something definitive about it. If you have very mildly truncated accretion disk, something at 10 RGs, I produced a simulation with for a 10 millicrab, just 1 kilosecond of exposure. You get beautiful data with it. And then you try to fit it. Let's say you're ignorant about the truncation, and you say, this is not truncated. I'm fixing the inner accretion disk at the ISCO, and I'm just trying to fit all the other parameters to the best I can, and you cannot come up with a good fit. This is not true when you do the same exercise with current instruments, even like NuStar, unless you have very long exposure. But STROBE-X with just 1 kilosecond of exposure will clearly tell you you're wrong, this is truncated. You can obviously do the inverse exercise as well. So I didn't have time to go into it, but it could be possible that with STROBE-X we will be able to actually measure both a spin and inner radius at the same time. This is a big problem because right now these two parameters are quite degenerative. They do a very similar thing to the line profile. So if you want to estimate the spin, you need to fix the inner radius. If you want to derive inner radius, you need to fix the spin. So you always need to assume something. And if we'll be able to measure both of them at the same time, that will be a big game change. So there is another problem that we have, and it's with the iron abundance. Both in AGNs and black hole binaries seems to, every time you fit reflection, there is a very clear trend to come out with, or the models require very high iron abundance. This is an histogram of a sample of AGNs and black hole binaries that I just collected from the literature. It's rather old already, it could be a lot better, but essentially you can see that everything peaks around 5 times solar, and we don't really understand why this is the case. When you try to, using the same RxD that I showed before, if you try to force the iron abundance to be solar and move all the other parameters as best as you can, you can't get a really good fit. It's really terrible, and I think there is also some kind of a correlation or dependency between the iron abundance and the inner radius that we need to investigate further. And maybe I don't want to say this. This is, I mean, for GX again, there is a whole family of solutions from a couple of papers using Nuster data, and if you plot them all together, they look like a mess. But you can see there are 2 big solutions. One is one's low truncation. The other solution wants high truncation, but the high truncation always comes with smaller iron abundance, with larger truncation comes with the small truncation, larger abundance. So there is some correlation there we need to understand. The iron abundance, I think, is very interesting, and it's been overlooked over the time. I think obviously there are 2 possibilities. It's real. There's actually more iron, and we have no idea why. I don't think that makes sense because we see it both in AGNs and black hole binaries, and there is no reason why both systems are going to have an enrichment of iron. If they're not real, then obviously there is something else happening. Could be some exotic mechanism that we don't understand. Ion levitation have been suggested. I don't think that's the case. Or there could be some key physics missing, like high density plasma effects again, and that kind of ties with what I was saying before. If we can have a very good coverage of the softband and the details, we can understand whether we're seeing high density effects or not. Just one slide on saying that the only place where obviously resolution matters is in the coupling absorption from reflection. This is an example for GX339 for one of the latest observations with Nullstar. These are observations done in the entire full orbit of the system, and what you see is a lot of changes in the absorption column within the orbit because this is a wind-fed system. So you don't see the details here, but there's a ton of absorption going on, and this is one good example where we might want the high resolution, but I need to do the simulations to see what XRCA will do for us. So I'll just finish here. I just want to say some caveats. I did everything in a rush. These are a relatively small number of simulations. Right, optimistic scenarios most of the times. I put the parameters that will give me more or less the best reflection spectrum, so that's not entirely realistic. So we need, the simulation business is complicated, it's very time consuming, we need to do a lot more with that. And some of the questions I already asked, why to stop at 30 kV, that was answered. Can we reduce the background? I think that might be the one limiting factor in some of the science we want to do. And as I said before, resolution to me seems important. From the point of view reflection, seems to be important only at the soft energies, not for the lab. If you have to trade, if you ask me if you have to trade area and resolution, I say just get the most area and don't worry much about the resolution. If you care at all, I put my simulation, the stupid script in GitHub. If anybody can use it or finds anything useful in it, just feel free to grab it.